Hi again. Okay, so it looks like we're racking up the lectures on the sequence section. Quite a few. We're up to lecture 8. In this lecture, I want to talk about monotonic sequences. And first, a quick warning. My definition is a little bit different than the book's definition. I'll tell you what that is as we get to it. But let's just go through what I've got as a definition here. So we're going to say a sequence is increasing if an is less than or equal to an plus 1 for each n. So in other words, we've got a1 is less than or equal to a2, which is less than or equal to a3, which is less than or equal to a4, and so on down the road. So the thing is you're getting points that are going up and up and up as you go further down the sequence. I'm going to say it's decreasing if it's the other way around. If, in fact, A1 is bigger than or equal to A2, which is bigger than or equal to A3, bigger than or equal to A4, and dot, dot, dot all the way down. So now we've got points A1, A2, A3, A4. It's going this way instead of decreasing in the usual sense, getting smaller. So we're going to call it monotonic if it is either increasing or decreasing. Okay, so let's just say, before I go on further, let's just say a quick difference between mine and the book's definition. So be careful with WebAssign. WebAssign's going to expect you to use the book's definition. But I like my definition because it's more general and all the theorems we talk about work with this. In the book's definition, they have a strict inequality here and a strict inequality here. I will call that strictly increasing if we have that strict inequality, or strictly decreasing if we have the strict inequality, or strictly monotonic. But other than that, everything is really about the same. Okay, so strictly if we get that strict inequality. Okay, now if you notice here, I have a couple of sequences, two of which you should recognize from the last video on bounded sequences. If you recall, this is the sequence. Let's write this out again. This is 1/2, 2/3, 3/4, and so on down the road. And we had written it as 1 minus 1 over n plus 1, right? And when we wrote it that way, we were able to see that as n gets bigger, this term here gets smaller, and so this whole term here gets bigger, right? First off, this is always less than 1, but second off, it's increasing. N over n plus 1 is going to be less than or equal to, in this case, strictly less than n plus 1 over n plus 1 plus 1. So the anth term is going to be less than the anth plus first term. So this is an increasing sequence. In fact, in this case, it's strictly increasing. Okay. Now this is one we saw before as well. This thing's going down to 1, right? We had rewritten this as 1 plus 1 over n, right? And we had noticed again before that as n gets bigger, this term here gets smaller, so this whole term here gets smaller. So in other words, our point last one is that it was bounded below by 1, but in this case, we've also have it decreasing. In fact, we have it strictly decreasing. So n plus 1 over n is going to be strictly bigger than the next term in the sequence, which is n plus 1 over n plus 1. So this is strictly decreasing. So we get a strictly decreasing sequence here. Okay. And now this one is not quite the same one as before. I wanted to do this one because it's kind of interesting, and I want to plot these on a number line. Okay, so let's get our number lines 0, 1, and negative 1. Let's use a different color here. Okay, so at n equals 1, I'm going to have negative 1/2, right? So this is n equals 1 here. That's not too different a color. Let's try that. Negative 1/2. That's at n equals 1. At n equals 2, I'm going to have positive 2/3. Positive 2/3. At n equals 3, I'm going to have negative 3/4. Negative 3/4. That's over here. At n equals 5, I'm going to have, wait a minute, that's n equals 3. I'm sorry, that's at n equals 3. I have negative 3/4. At n equals 4, I have positive 4/5, right? At n equals 4, I have positive 4/5, which is somewhere over here. You see what's happening here? I am bouncing back and forth. In fact, we know that n over n plus 1 goes to what? We know that goes to 1. So what I'm doing by doing this negative 1 is the positive portions are going to positive 1, right, over here. The negative portions are going to negative 1. This is just bouncing back and forth. First off, this is not monotonic at all. It's going back and forth. Secondly, it's not, in fact, it doesn't have a limit at all, right? Is it bounded? Yeah, it is bounded. It's bounded below by negative 1, and it's bounded above by 1. In fact, the least upper bound is 1. Least upper bound. Is equal to 1, whereas the greatest lower bound is equal to negative 1, but it's not monotonic. It is bounded, but not monotonic. The other two sequences we looked at were monotonic and bounded. It's quite possible to be monotonic and not bounded as well, like the sequence n is not bounded above, right? But it is monotonically increasing. So we can have really all of these situations. But why am I talking about monotonic and bounded together? I am because of this theorem, and this is a very important theorem. In fact, this is almost a defining feature of the real numbers, called continuity of the real numbers. Slightly different concept of continuity than you're used to. But the theorem is a bounded monotonic sequence must converge. Okay, more precisely, if it's increasing and bounded above, it converges to its least upper bound. LUB is least upper bound, and if decreasing and bounded below. Converges to the greatest lower bound. Okay, in the next video, I'm going to do an example of how we can use this theorem to talk about whether or not a recursively defined sequence converges or not, and if so, what it converges to. Okay, bye for now.